Hi, good morning. My name is Bernardo Tellini. I'm from Italy, University of Pisa, and I will give you some notes on the measurement of magnetism in composite materials. The main content of this short presentation is an introduction to magnetism and magnetic materials, some revisitation or consideration about the concept of macroscopic field in continuous media, and what is the meaning of measuring magnetic permeability in composite materials. Of course, it would be too much ambitious to give and to cover all the aspects of magnetism, but I hope to stimulate some discussion, recalling some basic concepts that are at the basis of the discussion we will have during this talk. Well, the historians still debate on when and where magnetism and magnetic effects were discovered for the first time. Possibly Thales of Miletus, 6th century before Christ. In 2nd century before Christ, according to the Chinese literature, we have indication of a compass spoon, but it is with the experiment of Ørsted that we have a relationship between moving charge, and magnetic field. Looking at reference books of magnetism, we are inhabited to find a very classical problem, that is the field in presence of a uniformly magnetized sphere. As you can see, you can recognize the typical lines of the field of a uniformly magnetized sphere. And the magnetizing field that inside the sphere point in a positive direction with respect to the magnetization. The magnetizing field is important, as you can see here at the right, in order to reconstruct the magnetic permeability as well as the magnetic susceptibility of the material. The other concept we have to consider in our discussion is the concept of macroscopic field in continuous media. This was introduced by Lorentz, and Lorentz in particular says that it is important not only to try to describe the field at a microscopic level, but to understand what is revealed to us, the behavior of the material at a macroscopic level. Where a macroscopic level means that we have to consider a spatial averaging of the quantities of interest over a region that is very large in comparison with the atomic structure of the material. You can find more references directly in the paper of Lorentz that is reported here at the bottom of the slide. In 1968 appeared an interesting paper discussing the possibility to study material which exhibited negative magnetic permeability. And it was around 30 years later by the group of Professor Pendry that it was proposed the idea of making a material which was able to exhibit such unusual magnetic behavior. The fact is, due to resonant condition, that the magnetizing field, the stray field, could be even greater than the applied field, and this could open the possibility to have unusual magnetic behavior, and in our case, to have at the end a negative value of the magnetic permeability. What about the basic concept of measuring effective magnetic permeability? Let's consider like an indefinite solenoid, here represented by the small circles, that should generate a magnetic field inside the region. Inside the region, we have here represented by these two parallel lines a cylinder, a conducting cylinder. Well, if the field is an alternate field, of course, along the conducting cylinder, these are two parallel lines, we will induce current. But if we would be able to close the cylinder through a series connected capacitor or something that acts equivalently, we could have some resonance. And looking at this expression, we can understand that close to the resonance, assuming especially a small value of the resistance R2 that is referred to the conducting cylinder, we would be able finally to have a large number here that means a negative value of the effective permeability. What is the effective permeability? We spoke about spatial averaging, but where are we making this averaging? What is the region? Let's look again at our representation. The external solenoid generates the field inside this single cell setup, where the matter, our atoms, we could say, is represented by the internal cylinder. Now, I have to measure, of course, the magnetic flux density through the cross-section of the external solenoid. I can refer to a cross-section because of the indefinitely long assumption of the solenoids, and so because of the uniform field independent of the zeta coordinate, assuming z is the coordinate of the axis of the solenoid. While the magnetic field, how can we measure the magnetic field? We can measure it by averaging the field outside, apart from the matter. That means in this region, we have not to consider the internal solenoid. As by definition, we have not to take into account the Amperian current. Thus, if we develop this calculation, and you can find more information here, you would arrive at such an expression. Here I propose a structured array. Before we had a single unit cell setup, and here a structured array. Without derivation, you can find in these reference articles that we arrive at equivalent expression of the effective magnetic permeability, and this because we have to take into account that the stray fields from the resonators has to reclose through the structure, and assuming a uniform reclosure through over the structured array, practically we can demonstrate that the single unit cell setup can be used in place of the structured array, where this is the region over to which we have to evaluate the magnetic flux density through a spatial average. This is the region over to which we have to spatial average for the measuring of the magnetic field. As I said before, outside from the metal. The equivalent circuit can be easily derived, but apart from that, for which I send you to the reference here reported at the bottom of the slide, the concept is again explained here in this 3D representation. The cell, in such a case, we have a structure not only plane but also in 3D coordinates. The cell is this hell gray, over to which I have to average for the measuring of the magnetic flux density, and this is the region over to which I have to average for the measuring of the magnetic flux, of the magnetic field. Just to suggest that to elaborate such a measurement is quite easy to implement a setup. It's a very basic setup. There's no problem to do that. And to verify, this is a basic concept. To verify this is a basic concept, that means to really understand the meaning of effective magnetic permeability, that can, in principle, opens to novel possible application even at industrial frequencies. As we can see now, we could obtain measurement are referred both to the single unit cell setup and the structured array, and they are practically undistinguishable. And we can have a negative value of the effective permeability even at industrial frequency. The imaginary part, as you can see, is representative of some losses. Of course, we have some losses because we are inducing current, and losses are unavoidable. We could have a discontinuity, of course, in the ideal case, to use an ideal conducting cylinder, resonator. Here we have our conclusion. We recall some basic aspects of magnetism, in particular the magnetizing field and the concept of spatial averaging over a representative region. In our case, the cell, and the resonator as representative of the matter. In a way, it is like our atom. This to finally discuss the measurement of effective magnetic permeability. Thus, I hope this talk in some way could be of interest for the audience and stimulate some interest and discussion. I am available for more information. Thanks for the attention. Goodbye.